talking about gravitational potential energy. It's stored energy, and it's based on the position of the object in the gravitational field. Basically, how high above the ground the object is going to be, or the zero reference level. That's what's going to give us our gravitational potential energy. When we're talking about elastic potential energy, then we're going to be stretching or compressing an object. So our stored energy will be in the object itself based on the elasticity. So how do I create potential energy in an object, right? Technically speaking, we're using a conservative force and it's doing negative work. So I'm doing work against a force that is not lost, right? Conservation means to not lose or to keep. So what is exactly a conservative force? It is a force that is not path dependent. And the two that we're going to be talking about are the force of gravity and the spring force. Okay, remember that the force of gravity is also known as the weight of the object, just in case you see that along the way. Just like kinetic energy, potential energy is a scalar and it will never be negative. If you have a negative energy, that we will consider as work. Okay, anytime you see a negative energy, that is going to be your work. So let's jump into gravitational potential energy. The gravitational potential energy, PE, with a little g next to it, is stored energy of an object that is above the zero level, meaning it has the ability to fall. Now, in the past, we have talked about free-falling objects, so we're going to keep that information in our back pocket here for quick access, because we're going to apply that as well as our knowledge of energy. To solve for the potential, you're going to multiply the mass, which is m, times g, which is the free fall acceleration without the directions, just the magnitude only, times the height, which will be y. In this case, sometimes they use h, sometimes you'll see a delta y. It's all the same thing. So multiplication, and if you look at it, it should be kind of familiar. If you see here, it says that the work done by Fg, or the negative work done, is this going to be equal to the potential energy. Okay, the work will be negative, but the potential will be positive. They have the same equation, right? Because Fg is the same thing as m times g, and oh look, m times g. Okay, literally the difference is no direction. Okay, we don't care which way Fg is going, we don't care which way delta y is going for the potential. So let's look at our first example. A mass of 32 kilograms is lifted to a height 9 meters above the ground. So we have our mass of m, our height of y, and g is always 10. We are going to plug those numbers into the equation and solve for the potential. Okay. Pretty easy. The math in this is super easy. It's the conceptual stuff that sometimes can get a little bit tricky if you're not paying attention. So we have 2,880 joules of potential energy. Part B says how much work was done by the gravitational force when the object was being lifted. So we know the force of gravity is going down, and the displacement, right, our delta y for the object being lifted is in the upward direction. They're in the same plane, opposite direction. So what happens? Well, that makes our work negative, and we know that the work is going to be equal in magnitude, opposite in direction of our potential. Okay, because they're going against the force of gravity to lift it. Part C, what effect does the work have on the object's energy? The work done against the conservative force, aka the work done by gravity, or in this case going up against gravity, creates the potential. The whole point of doing that work is to create the potential. So now I'm going to let the object fall down back to the 0 height, and I want to know how much work is done. Well, now the work is going down, right, the direction, because the force of gravity is down, the delta y is down. If those two have the same direction, then we have a positive work done. This is back from last chapter, or last quiz, whatever you want to call it, right? If the force and the displacement go the same direction, then it's positive work. If they're in the same plane but going opposite direction, then it'll be negative work. So the whole point of doing the work and creating the potential is then to get to the end result of the object being able to fall, which then creates kinetic energy. So keeping that in mind, we're going to analyze the situation and look at each individual component or quantity that we know about our object. So we know that we're at a height 9 meters above the ground. And before it falls, the object is at rest. So all of my energy at the maximum height is potential. Right, we're not moving yet. As the object starts to fall, the height is decreasing. And if the height is decreasing, that means the potential must also decrease because they are completely dependent on each other. Okay, they are directly proportional. So as the potential is decreasing, that energy has to go somewhere. It doesn't just go poof, magic and disappear. Okay, you guys have heard the law of conservation of energy before. You've been learning it for who knows how long, years and years, right? Energy cannot be created nor destroyed. It just is transferred from one form to another. So if my potential is decreasing, how much potential I have is decreasing, and my height is decreasing, where did it go? Well, remember, as the object is falling, it's speeding up, right? Our rules of free fall tell us that our object is speeding up. It's moving. So if there's motion, there's kinetic energy. And if it's speeding up, we know our kinetic energy is increasing. Okay, so that's what I wrote here. The potential is decreasing as it falls. The height is decreasing. The kinetic is increasing and the speed is increasing. So what does that mean? Well, that means our potential is turning into kinetic as it falls. Once it reaches the 0 level, the height no longer exists. So there's no more potential. If there's no more potential, that means all of it was converted into kinetic. Okay, now I want you to keep in mind, whenever we're talking about these, we're talking about ideal situations. No friction, no air resistance, no heat transfer, It's ideal, 100% PE to KE conversion. Okay. So it's asking us, how fast is the object going? Well, because our potential turned into kinetic, I'm going to use now the kinetic energy equation. And I'm going to solve. So how much kinetic do I have now? 2,880 joules. Because I had that much of potential, and it all transferred to kinetic. My mass doesn't change. And now I can find how fast, or the speed. Dividing, and then taking the square root. Our speed is now 13.4 meters per second. Okay, so let's recap gravitational potential energy. In order to create gravitational potential energy, you must do work against the force of gravity, right? The conservative force, in this case, is the force of gravity. You're going to lift that object some height above the ground, doing work, okay? Negative work creates potential.